the subsidiary of ICAM is International ICAM, the International Institute for Complex Adaptive Matter, sponsored by the National Science Foundation. And our basic scientific goal is to elucidate the organizing principles of emergent phenomena in matter, as it says up there, partly facilitated through workshops in schools like this one, which will be focused around the questions of interest and heavily discussion-oriented. In fact, I'm going to request that each speaker try to allow for at least a half an hour to 45 minutes during their lecture for discussion. We'll try to be strict on that, even with me. What do I mean by emergence? Emergent phenomena are phenomena that owe their existence to interactions between many subunits, but whose existence can't be deduced from a detailed knowledge of those subunits alone. For example, how can a collection of molecules think about what molecules are? Complex adaptive matter are materials which exhibit emergence. Examples are novel superconductivity, amyloid assemblies of proteins, multi-carrier generating nanoparticles for photovoltaics. And ICAM's mission is to search for the organizing principles of emergence in complex adaptive matter. I'll just show you a few highlights of ICAM. One is that ICAM began with 9 founding branches in 2002 after a few years of existence, and now we are up to over 50 branches representing over 60 institutions around the world. And you can see the branches pop up here as little circles on this world map. In fact, since this slide was made in early January, we've added, I think, 3 more branches to ICAM. So it's a big worldwide institution. We get money from many places. We get money from the National Science Foundation, which is the sponsor of this meeting right here. We get money from our members. Each member contributes through either direct cash contributions or through a in-kind sharing to the operations of ICAM. We also get some money for domestic operations in NSF, some money from Los Alamos, and some money from foundations. And I think I'll just move on to the next slide here, rather than go through the details of that. Our principal activities are to fund workshops on correlated electronic matter, biological matter, and soft matter, and advanced school or workshop annually in Cargés, Corsica. Now we have an annual school in Rio de Janeiro, and we're starting a school in Bangalore with the Nehru Institute for Advanced Scientific Study. Something that might be of interest to the junior scientists, both from the US and from Brazil, is that we sponsor exchange awards in which you can go for 2 to 12 months between 2 different groups to enhance or nucleate collaborations between those groups. And the exchange awards pay per diem plus travel. We also have junior scientist travel awards for short research visits, and we have extensive web pages and so on for communication. And in fact, here's our web page listed right down here, in case you didn't already know about it. Just to give you an idea of where the exchange awards have gone, this is a time-lapsed photography. And the exchange awards have funded such science as this piece of science about copper oxide superconductors, which made the cover of Science magazine last year. I won't go into the details because it's sort of abroad from this meeting. We also fund these travel awards, and the travel awards also have gone sort of all over the world. And here's a quicker time lapse. The travel awards can be for short conference visits, or they can also be for research activities. For example, Avinash Kane from UC Davis and Livermore has used a few different travel awards in order to go to the synchrotron lab in Berlin and build an apparatus for time-resolved protein folding studies. So this is just to give you an idea of the kinds of activities that ICAM is involved in besides supporting schools like this. We're highly oriented towards interesting science, exchanging, networking between institutions, and particularly focusing on young people like yourselves. So I hope that you would enjoy this meeting, and with that, I guess we'll move on to the next person.
Professor José Onushik will give the welcome address.
Good morning to everybody. First of all, I want to thank Daniel and Elisa for doing everything. Jerson and I are just taking the credit for it, but we have not done anything. Elisa and Daniel did. Elisa and Daniel did a great job. And I'm happy to sort of be on the side, helping this school to get organized. We're going to have a great week here. And what I really want, since we are also BPF, the Centro Brasileiro de Pesquisas Físicas, is to get people here, particularly people that come from a physics background, to understand by the end of the week, in a good way, what we mean, the difference between biophysics and biological physics. I'm going to start to work on it. I think it's a very important distinction because physicists are making a major contribution to the life science now, in a way that is not just sort of a supporting technique for the life science, but it's really the idea of using the physics of complex systems and physics techniques, and in certain ways, just a physics attitude to look for underlying principles governing complex phenomena. And that's what differentiates these things, to basically say, what is the intellectual obligation or intellectual gain for physics to study life science. But we're going to have fun. Thank you for coming.
The FAPES director, Dr. Justin de Lima, will give his address.
Well, first of all, I would like to welcome all the people that came from very far away, and the speakers, and also the Brazilians, and so also to welcome the local Brazilians also here. So I have two hats. So first, as a member of the organized committee, my participation is very little. I think we're distributing more or less half and half in nothing. Very little between myself and José. And so all the credit should be also given to, as José mentioned, to Daniel and to Elisa. And so I think it would be, like José, I agree that we have to, I think it would be an opportunity to merge these two, in principle, similar areas, but maybe sometimes a little bit distant. So the people from with biophysical background and people with what's called biological physics, that usually they work more in physics. So I think we have the program is very good and very appropriate, like Daniel pointed out, that we have a lot of time for discussion, to questioning, going from the basic principle to recent data and different interpretations. So I think that would be a key point in our meeting. Now, changing my hat, I go back as a scientific director of this funding agency. When Elisa came the first time to talk to me about ICANN, I said, well, I couldn't understand. And then my wife was just coming back. She's a biochemist too, and she's the director. In fact, she's my boss, she's the director of my institute in Rio de Janeiro, at the University of Rio de Janeiro. And she was just coming back from a meeting in the amyloid field that was in Switzerland. That was 2 years ago, right? And so I started paying a little bit more attention to Elisa. In fact, Elisa is part of a team in our funding age, because she's what's called a coordinator of area. So she takes care of all the physics and grants in the state of Rio de Janeiro. So I give a lot of trouble to her because it's quite the main community, especially in Rio de Janeiro, because we have several departments and institutes of physics, and also we have this very important institute that is the BPF, Brazilian Center of Research in Physics, that is, I think it's more than 50 years, right? And so it's famous by having, so I think the institute had Professor Feynman here for almost a year, in the 50s, I think, something like that, or early 60s. So, in fact, one of the caps in his book, I was joking, Mr. Feynman, he talks about the good time he had here in Rio de Janeiro, with the samba, the carnival, and so. And on the other hand, he also, from what he said in this book, also he was the time that he worked a lot, especially, well, in the area of his field, but and as we know, he pointed out a lot of the future of physics and especially of nanotechnology and nanoscience, and so we'll be remembering a lot Dr. Feynman here. So anyway, the scientific director of the funding agents, the president is not here because he's in Japan now. In fact, there was in the newspaper the governor, and he was just on the side, I think one of the newspapers today, they are in a visit to Japan, but he asked me to bring also the welcome words to all of you. So I'll be around all the time, and so I'll be giving talks tomorrow, so I'll pay attention today a lot, so I can fix my talks tomorrow. And so I wish again good stay, both scientifically and also time for leisure in Rio de Janeiro. Thank you.
Finalizing the opening of this meeting, the word is back to Professor Elisa Barros-Zetovich.
This order of speakers is a bit strategic because I did want to know how many minutes I would have to speak with you a bit longer. And the question is, sometimes I ask me, why are you so much involved in organization of meetings and schools and so on? And it gets back to the first conference I have organized, was Latin American Conference on Most Power Spectroscopy, and I realized how important it was for the Brazilian students to be able to listen to some famous scientists in their field. And you know, Brazil is very far off of the center of producing of science, so sometimes it's difficult to give support for the Brazilian participants to go abroad, and Gerson knows about that. So since then I have tried to organize meetings and conferences so that give the opportunity for Brazilians and mainly Latin American to participate, and this is, I think it's very important. When I was addressed by Piers Coleman to work, because ICAM wants to open a link in South America, and so they addressed me to do that, and I was work hard to get support from Brazilian side. I went to our kind of NSF, but they said that it was too complicated, you need to sign contracts at government levels, very complicated. I came to the director of our institute, that's the National Institute of Physics from the Ministry of Science and Technology, and I asked them, okay, look, that will open this opportunity for many institutes in Brazil, but he did not want to do it. And then I went to Gerson, and he told you, and I was very glad that we were able to start. So last year we have one school on emergent strong correlated system. This year is the school, and the next year should be one on soft matter. And if we can reproduce the results for last year, I think it will be very important, because I think the main point is, of course, the content of the school, that you get to learn more about the topic, but also the interaction about young people that will be the future scientists, you know. And if this interaction can be established at such level, it will be certainly one contribution for future collaboration. And that is, Americans come to Brazil and know how they can be hosted here, how they can work, and also the Brazilians can go there. So I think, and at the same time, we have prepared a program that's a kind of balance, that you also can get some feeling what's the life in Brazil out of the labs, you know. So on Wednesday, we have an excursion that go to the Christ, to these statues, and then we have a meeting for dinner all together in the barbecue house, very young. And Thursday we also have a program for the night, so I think it will be close to the end of the school, and you can. And okay, so our institute, I think, is very proud to be able to host this series of school, and if they are successful, maybe we can go to a second term. And I think maybe we can make you can come back in the future. And of course, I want to thank the sponsor, because we can work a lot, but we don't have a sponsorship. It will be very difficult. I can give a strong support. FAPERJ promised so far that will give strong support. CAPES, the Brazilian Institution for Ministry of Education, and also the CBPF has given all the infrastructure and also some money for supporting the organization. So I wish all of you a very nice week. And any problem you have, any wish you have that's related to the school, please you can address our secretary, and hope we can help you. Okay.
We invite the members of the opening table to return to their seats at the audience in order to start the school program with Professor Onushik talk.
Good morning, bom dia. The idea on this first lecture is to tell you a little bit about the biological physics of protein folding and protein function, how we go towards that. I think if you notice the school, if you notice the program of the school, we'll be doing a lot of work at the molecular level, but I think you're going to have several lectures where we're trying to make the interface between the molecular and cellular level, talking about a little bit of gene networks. So I think we are sort of this interface. I think the idea when I talk to Daniel is that basically, why don't we move all that way? That's kind of interesting because on the area of physics applied at the molecular level, there's been a lot of work in Brazil, and some people are moving to the cellular level. It's becoming a very hot topic, particularly a lot of theoreticians have been moving that. So it's sort of an interesting mix to do here, okay? And don't worry about this thyroid, because I really want to go to this slide, and it's going to take me a little bit of time to go over what we have here. And the idea is, how many people here ever heard about the protein folding problem? Okay? So if you ask people, what is protein folding? And how many people here believe that physicists should care about the protein folding problem? Right? Oh, we shouldn't be in this room if we don't believe on that. Okay? So, with that in mind, let's try to go through the definition of the words and try to put on your brain how we work and why basically the protein folding problem. There's something that, if you read the literature, it's called the new view of protein folding. And this new view comes when basically people that come from a physical science background, mixture of theoretical chemistry and theoretical physics and things like that, got the physics of complex disorder systems, and use all that technology to fully address the idea of how the process works, and come with the concept of what's an energy landscape. So today, I hope on the end of this lecture that you understand why protein folding problem is a good problem in physics, what we mean by the landscape idea, right? Basically, how this concept that you know they come from areas in physics like frustration are also important here, and why these things have been useful to actually connect to a lot of new experiments that have been done. It's not just a total abstract, it's a way that basically developed a quantitative background. Something that's basically is just not only words but equations that sort of drive the entire system. So let's start with the definition of the problem of what is protein folding. If you open any book or any biochemistry book, or you ask to anybody that has been on this field for a long time, they're going to tell you that protein folding is the problem. Proteins are a heteropolymer. That means they are a polymer. A sequence of several amino acids is a heteropolymer because because the amino acids are different. So if I draw like beads here on this chain, this necklace of beads, you have different kinds of amino acids. So when people tell you here's a protein with 120 amino acids, they give you a list of amino acids. And alanine, glycine, threonine, they give you a list of amino acids. And the old problem was the following thing. Because of an old experiment by Amstel on the 60s, and he got the Nobel Prize in 75 for the protein folding problem. I'll tell you why that's a very important experiment a little bit. In terms of attitude of looking at the problem, people knew that you put a protein in some physiological conditions alone was able to fold alone without any help, without any machinery. At least that's true for many proteins. There are few complicated cases that's not true, but for many proteins they could fold alone. So there was this ability of self-assemble. So the idea is, if the proteins are able to self-assemble alone in physiological conditions, all the information that it needs how to fold has to be on the sequence of amino acids. There's no extra information. So the protein folding problem became a problem that people said, given a sequence, can I predict the tertiary structure, or the three-dimensional structure of this protein? Now, this problem appears very complicated, but that's not the most complicated problem. When the physicists jumped in, they did something that basically people in biology didn't care. They said, but there's an interesting thing. If I come here and I give you a random sequence of amino acids, you just go, and you make a random sequence of amino acids, that will most likely not fold into a unique three-dimensional structure. So the question then raised, what came on the old days when people started to think about this problem, this actually, see how this field is actually young, this is a field that when this question started being asked in a serious way, we're talking about mid-80s, early 90s, that's when people came to this thing. The question is, given a sequence, is that sequence able to fold? Or in another way, what I'm trying to write in a very simple way here into this slide is, what differentiates a random heteropolymer? That means, if I get a random sequence of amino acids from the sequence that are able to fold. And that was a question that you're not going to find in any biochemistry textbook. Actually, all the biochemistry textbooks are wrong. Because you open a chapter in proteins, they say that proteins are a heteropolymer of amino acids. And very few heteropolymers. Oops, I have to stop this thing. I'm on my fingers. He is saving me here. I'm just turn this off. Again, I'm sorry. Just give me a second, otherwise we don't have to fight with this. That's the problem. Oh, I should behave. Okay. So let's start with this idea. So let me start first with the idea of frustration, and then I'm going to write on the board a few equations just so that you can get a little bit of feeling how that all started. And then we get a feeling about dynamics and equilibrium properties into a landscape. By the way, Elisa was talking about Amos Bauer school here in Rio. Just for historical reasons, since we're talking about proteins and landscape, the first person to introduce the concept of landscape into proteins was actually Hans Frauenfelder, who was a very famous person in Amos Bauer. So you see that there's this tradition of interacting these two things. Hans actually has a very famous paper in 1975 with Bob Austin, where he introduced the concept of landscapes and proteins and things like that. I will tell you that that's sort of the real first paper of what I call physics of proteins. So it's just for historical things here. Okay. So what's the difference between a random sequence and a protein sequence. Okay, so let's imagine what happens is the following thing. Let's imagine we think as a physicist, how would I characterize a heteropolymer? So let's think about the simplest heteropolymer I can do. I have two kinds of peaks. What's not a bad idea for proteins, because you know that the lower end, we always can break amino acid in hydrophilic and hydrophobic, right? So there's sort of polar groups and oil, right? So basically, and they don't like to mix. And so if you think about how the proteins fold, you could imagine that what you have is a sequence. And the sequence has hydrophobic and hydrophilic groups. And as you know, as you mix oil and water, basically the hydrophobic groups, the oily groups, they are trying to avoid water effectively. So what they try to do, they try to get as close as possible to each other. So the goal of these things when you mix oil and water is to phase separate. So what happens? Oil and water try to separate from itself and minimize as much as they can the interface between them, because it's a big price of this interface of having a hydrophobic group next to an oily group. So that's what they try to do for a group like that. But proteins have another situation. Life's not as easy as just mixing two things, because they are polymer. That means they are connected. So in a way, they try to separate from each other as much as they can. Right? They try to separate as much as they can, but there's so much they can do. At one point, they cannot really completely separate, because you have a polymer doing that. So what happens is that you're going to end up with a few interactions where you have groups of different color close to each other, even so they don't want. What the things are trying to do is to make all the contacts, blue with blues and greens with green, hydrophobic with hydrophobic, hydrophilic with hydrophilic, and try to minimize. But some of them you cannot do it. So what happens here is that since you cannot do these things, since you cannot separate these groups completely, you end up with a few interactions that are not satisfied. And that's the concept, in words, of what people call frustration. If you look at the low energy states of the system, what I'm going to call the global energy, if you try to minimize the global energy, the total energy of the system, the states of low energy of the system may have local regions that are unhappy, that have high energy. But there's no way you can globally minimize all the energy. So that comes the concept of frustration. You cannot satisfy all the interactions. What's the consequence of that? The consequence of that, if I draw all the possible energy states here, and this seems to be a scalar, this is energy, here is some similarity parameter, you're going to have states, low energy states, that are very different. But it's still low energy states. And why they are different? They are different because these are states that they are the lower possible lowest energy state. But where the wrong interactions happen, they are different. Right? So basically, it's a situation that happens. I always like to make an analogy, like my wife teaches kindergarten. So if you get kids at kindergarten when they're 5 or 6 years old, you know at that age, boys like boys and girls like girls, right? There's a phase transition later on. But at that age, that's the way it happens, right? So the boys, they don't want to see any girl close to them, the other way around. So if you're the teacher and you get all the kids and you tell them to give hands, right? And basically now you use your power as the teacher, so you decide the order of the kids. And now you tell, get close to a friend. Every boy tries to get close to a boy, every girl tries to get close to a girl, but there's a couple of slow ones that don't do it, okay? In proteins, if I imagine my problem here, if every boy and every girl were theoretically the same, no special strains, what happens is some local fluctuation or situation or how you start the problem, you may end up with different configurations. And you end up with a few boys and girls together, even so they don't want, because they're not fast enough. And that's exactly frustration. It's a frustrating interaction. It's a lot different, right? Because you're in a situation that you wouldn't like to be. So, if you think about it, the random heteropolymer, that's exactly what the proteins don't want to do. So if you have a random heteropolymer, you start to move on states like that. So when people wrote on that, let me write you a couple of equations just for fun, how it moves. People came from spin glasses, and people all probably heard from spin glasses that that this is the situation that you have. So how people brought this problem to proteins? I have an expression here, what I call TF and TG and things like that. How these terms come about. So I'm not going to do the heavy equations here. We have a few references for you where you can go after and spend as much time you want to. But let's try to put the idea. When people came from spin glasses, there is a great piece of work that started along several years ago by Derrida and several people in France, what they call the random energy model. And the random energy model is how people start to use with proteins, in a sense, to believe that you have a system that's so random that all the energies are uncorrelated and everything is uncorrelated. So I'm going to say that you have a system here that's very random, and in a sense they have random energies, and they have random connectivity. First of all, this is not totally true, in a sense that they states are connected to each other. As we do dynamics into my system, they don't have necessarily anything energy. That's not true. You can easily start to have correlation. The system people have done by many years, but to zero order picture, that's a great thing. So let's try to see if I can try to do the couple equations just for fun here. I don't want to go too many of them, but let's try to get a few equations for fun. So let's imagine I have a random system. Here's my head to polymer. And let's imagine that I could enumerate every possible configuration. So I came here and I enumerate every configuration. Okay? I'm not telling you about energy yet, but I enumerate every configuration. If it's a continuum model, I'm going to have to give you some resolution. A lot of this work was done on lattice. On lattice, I can literally, if I have something that's moving on a lattice, but assume that I have some resolution and enumerate all these things. Okay, in a sense, that's not only states. So what that means that a protein, as it's moving around, is moving between conformations, and it's jumping between states, right? And basically that's where you're going to get the lattice state. So if I have these small states that are jumping between them, you try to put this equation. Okay. So now what's the next thing I'm going to do? So now let's put a number. Let's say that this total number of states I have omega states, large omega states. I could have any other number, could put large n. That's the total omega of anything. We have a large number of states. Now I'm going to tell you that since this is a random system, I have to define my energies. And just for lack of a better thing, I'm going to say that my energy, we can put around 0 or any number. I have an average energy, okay? And has a Gaussian distribution of energy. So if I get my total density of states, n of E in a random energy model, these are states where, let's actually call this energy here, just for lack of a better name, let's call this average here like a 0 would be any other thing, just so you don't believe it has to be 0. You can have a typical thing to be collapsed positive, okay? And my density of states, n of E, is going to be my total number of states, just for normalization. And since it's a random model, and I told you it's Gaussian, right? So it's basically E to minus E minus E0 squared to delta E squared. That's the distribution, right? So if you have a system, if you have a random Hessian polymer, that's a very important number. That's what's the typical energy going to fluctuate with some normalization here. Okay? So that's a great system because it gives you a little bit of the feeling of what the system is all about. And why I'm bringing this up, you're going to see very fast, because as people talk about traps and randomness and stuff like that, I'm going to tell you how we try to relate kinetics and thermodynamics. Okay, the first thing you notice in a system like that is the following thing. Basically, that if I now try to plot my entropy for the system, I'm going to tell S of E is going to be log of these numbers here. So it's going to be just right here. It's going to be log of omega. I'm going to just ignore this for the time being as a small number here. Minus E minus E0 squared over 2 delta E squared. Okay? So that's my entropy. Okay, that's just compute the logarithm as a function of energy here, right? So if you come from physics, that's what I say, you're working the microcanonical ensemble, just write these things in terms of energy. Why that's great? Because that tells you something very important in proteins. That's the following situation. If I plot this entropy S of E, okay, what you observe, this entropy is a number like that. But that's a particular number here that I'm going to call EG, that I'm going to call the glass energy, because that's the system when my system collapses. The first approximation tells you that when I'm here, I have a large number of states, but there's a state where my entropy goes to 0. Means I run out of state. So it means when you're getting close to that energy, you get to that point. Okay? So this is the point where you say, so what happens? If I have a system at high temperature, what happens with a system at high temperature? See, now, let me just go one step back. At this point, observe how important this omega is. Because that tells you how many states are available. When you're talking about a problem like folding and a problem like a glass transition, you have to say how many states you have and are you running out of states. Okay? So I have this situation here for you that I just want you to keep that in perspective. You're going to listen a lot about traps, so let's think about this situation. And that happens for the protein also. So when you're in high temperature, the protein is happy, has lots of states, it's just moving around. But at one point, as you start to lower the temperature, what starts to happen? You start to populate states at a very low temperature. And I'm going to give you a number here, I'm going to write it tomorrow for you, I'm going to tell you. And you ask, when that happened, at which temperature do I run out of states? And the temperature that you run out of states is very simple, basically. If you remember now, I can compute the temperature just by remembering that how you go from canonical, from microcanonical to canonical ensemble. I come to you and say, when do I run? I run when I hit EG. That means S at EG is when this goes to 0. Right? So I can compute that from here. ln of omega minus EG minus E0 squared over 2 delta E squared. That's equal to 0. Right? That tells you what's this energy. You cannot go below it. Right? You cannot go below it because that tells you that you're running out of energy. And now, if we go back a little bit to physics, remember your course in statistical physics, how you're going to do it. To get the temperature, therefore, all I have to compute is derivative at this point here. So I know that my temperature here, that we call Vg, remember that 1 over T is going to be what? In this case, since I have no other variable, is dF dE. Right? So basically, all you're going to do is now to say that 1 over Tg is the derivative at Eg. So you can figure out. So in a very simple system, you can start doing estimates. In the old days, when Peter Wallace worked with Hans Raphael, you can actually come up with very good numbers. So the interesting things is basically, you can get typical experimental numbers for fluctuation, relate these to temperatures, how these numbers 200 Kelvin come, how many states you have, and the argument comes out of this line of arguments. Now, this is what you learn. So that tells you the first thing what happens if I have a random heteropolymer. So now it becomes easy for you to understand. Tells you that basically, if you think about the words that you hear about exponential and polynomial, that's not the best word for protein because it's still a finite system. But in a sense, it's basically you have a statistically large number of states. And if you have a system like that, and my total energy here will be some E0 with some fluctuation delta E. If I told you, basically, you could do a problem for yourself. You can say, if I have a typical interaction, attractive, repulsive between two things, and you write in a random way, you can come up with values like that, right? You expect that basically the typical energy goes with the fluctuations and the square root of this energy, so you can do the game, but let's not worry about that right now. But you can do this sort of randomness into your landscape. And then, as you start lowering the temperature, now you may end up trapped, or what we call a glass transition. In a protein means you're going, in a heteropolar means I'm going to get trapped on a low energy states. If you see here that I cut the state here, it's just to give a feeling for what's exponential. Exponential tells you go from something you have a large number to a finite number of states. That's what entropy zero here means, in a sense. You're running out of states, and that tells you, and that gives you the temperature that you run. Okay, now, that's the glass temperature, and that means whatever happens to a system here, if you want your system to be able to have some kinetics and to be moving around, you want to make sure that you're dealing with temperatures above this Tg. So every real protein, the system has to run on temperatures above Tg. Otherwise, you run into trouble. And there's a beautiful literature coming from statistical physics where people add correlation and add other things, but they move into this idea if you're really interested. Why I'm telling you that? Theoretical work in protein folding is just not only simulations. So you're going to hear a lot about simulations. There's a lot of beautiful analytical work. And that's one thing that base physics can contribute a lot. Actually, it's very hard to run any simulation or modeling if you don't have some theory that sort of guide you on the background as you're developing those models. Now, let's go one more step here that I want to say that people learn. Now, what happens is when you are on temperatures like that, you're jumping between these states. So you're moving around a landscape. And I will not tell you, I'm going to assume here, and that's by this, if you ever work with a spin glass literature, there's a temperature where they call TA, this is an activate temperature to see if you're jumping between minima or not. I'm going to assume you're jumping between minima here. The run energy model is a good approximation. You're jumping between these minima, but how is the dynamics moving around this minima? Because you have barriers. So you can estimate this barrier. So let's put a feeling for you in a run energy what's there. You see, if I ask you, if I have a system now at a particular temperature, what's the average temperature? What's the average temperature? If my temperature was infinity, then you'll be uniform distributing these things. But my temperature is not infinity, so you know basically what you're going to do here. You're just going to do what? You're just going to compute as we're going to do, right? Basically, you're going to do energy times the number of states, my n of E, times e to minus e over kt, d, integrate that, and my normalization here, just ne, the normalization to make sure you're normalized. Okay, so you can compute your average energy here. As you compute your average energy here, what you're going to notice, just out of curiosity, I'm not going to do the algebra now, but it's going to be a number of the order minus delta E squared over T. Maybe there's a 2 here, I don't think there's a 2. That's the typical energy, as expected, right? Basically, if you have infinite temp, E minus E is going to be equal. Let's be precise here. E is going to be equals E0 minus that. Okay, so if I look the same, the temperature was infinite, would be E0. Otherwise, you start to come to a lower temperature here. So what people notice when you look about kinetics, say, if I assume that my system is connected, what happens? Most of the time, I'm going to spend on energy, typical energy, that's equal what? To the average energy. Right? But when you try to jump out, when you try to, so if you have an energy like that, that's where you have. If you fall in a minimum, the typical energy of a minima here is this one, into this random energy. But when I move out, I try to go to a state that's connected to me. And if I try to go to a state that's connected to me, what happens? I go to a typical state, not to a state of, and a typical state is what? That is energy of about E0. So you always have a barrier. In a typical move, you have a barrier. That's a great idea. You have a barrier of what? Delta E squared over T. That's the typical barrier you have. You have energy, right? You're down here, right? Your average energy, you have this barrier. This is the average. Right? Your system is there, and that's the typical barrier you're jumping at a given temperature. Right? So you're getting from a state, and you're jumping from a state like that. Just to put it out. So what people learn from that is that normally you have an activate process. Right? You have an activate process. You have all these states next to you. Okay? And what you have is what people can tell you, that now you're going to have a diffusion in the landscape, jump between these minima, but your diffusion coefficient T, I'm going to call that D0, some prefactor that gives you the typical dynamics, but the temperature dependent of these prefactors is the energy barrier, delta E squared over T, so you get delta E squared T squared. Okay, so that's a great situation, because now we get into a situation that basically, now you are connected yourself into a situation that puts you. And that's what tells you that people call, and it's a word they would use in physics, people have been used that in biology for a long time, what they call activated dynamics. Right, so now you see the concept of the landscape becomes clear out of a very simple piece of theoretical physics that tells you you're moving a landscape, you're jumping among minima, and how you're jumping, how the activation came from a very simple algebra here, right? I just have to figure out what was the typical energy and what was the typical state. And they're different, right? Because normally minima is this one. So this put in perspective, and that gives you a real kinetic view of how it all glasses. For states here, and your temperature comes down, and you have lots of neighbors. What happens? At high temperature, you go over its activate dynamics. The temperature gets lower, what happens? Oh, you try to go up, but it's very too high for you at low temperature. So what happens? The system rather spend a lot of time to look at every single neighbor and figure out which is the one with the lowest barrier, and you jump that one. You jump the other one. As you see that, now you get trapped on that particular circuit of lowest barriers. So that's exactly when your problem stops being ergodic and become glassy. Right? So you go for a situation that your temperature is high enough, you just jump to a typical neighbor, and that's the most likely event. If the temperature gets very low, you don't jump to a typical neighbor. The thing becomes so overwhelming for you, that's the glass transition, that you rather search for what's the easiest way up. Right? Basically. So you actually go around. So the question is, do you pay the energy price, or you pay the entropy price? Let's look around and find your neighbors. Okay? So with that in mind now, you are in good shape. Now what happens when you do, that's the run of heteropolymer. Say, oh, wait. You have been telling me for over half an hour about a run of heteropolymer. But that's going to give us all the good feelings that we need to move towards proteins now. Now, what a protein wants to do is exactly not that. The protein doesn't want to be a run of heteropolymer. The protein doesn't want to be lost or have many possible solutions at low energy. The protein wants to make sure they can find one state. Right? So the protein doesn't want to be a frustrated system. So what the protein wants to do is to get one of those states. Okay? One of those states. And pull it down in energy sufficiently low in such a way that now one of the states become more likely to be occupied than everything else. And that's what I call a stability gap. So
when you draw a protein landscape, in addition to these random states here, I'm going to have another sequence of states that are not random, they're becoming more and more protein-like, bring you down to a lower energy state. The system is selected by nature in such a way, the ones that really have a tail here in low energy, that you may end up with low energy states here. I draw a few of them because you don't have just one of them. It's not like a golf course is a mini. Otherwise kinetic would be a problem. We're looking for a state that is. So now what you try to do is to make sure that you have a state, and this one now we call this delta E, that's what we call a stability gap there, right? I'm going to write delta E here now, is my stability gap. And that means, but there's one thing I learned by being in many situations, and people say you need a large stability gap. But remember, every time someone tells you large, you say stability gap is energy. Energy has units, and energy has units. You cannot just say large or small. You have to be large and small compared to something else. Right? So the bottom line is, you want to make sure that this energy gap is large enough, in such a way that this low energy state here, that's my protein state, becomes occupied in a temperature that's high enough compared to what? To my glass temperature. Because if I have to go to a lower temperature, my system will get trapped kinetically before it has a chance to find my lower energy state. So that's what, you see, the beauty of these things here is that by assuming this randomness into this process, I was able to come with sort of a equilibrium and distribution arguments with a kinetic picture. That's not 100% correct, but give you a lot of guidance as long as you don't believe there's any particular connectivity problem or geometry, and we'll be talking about geometrical problems. But that's the next step. But let's stay on the energetic situation. Here I told you, as long as you don't believe that you have any major geometrical bottlenecks here, this line of argument helps you. So that means that basically your temperature has to get stable. And that's what we call the folding temperature. Okay? And the bottom line for your folding temperature is to say that is basically what happens in the system. If I have a system now with a stability gap, means what? If my temperature is very large, then I'm moving around this large ensemble of states. My temperature is very low, you come to the low energy states. So TF, the temperature that brings you between the disorder and the ordered state. Right? So basically, the larger the gap, the easier it is for you to do that. And like I said, you want to make sure this folding temperature, TF, is larger than Tg. Right? And basically, and I told you exactly that means Tg here for us, is basically when you get kinetically trapped, you can never find your state. So the problem of proteins folding has two parts. Right? And that's where these terms Tf and Tg come from. There are many other representations in there. And the things that happen, so what you notice is the protein folding problem is like many optimization problems that you have in life. This is a major optimization problem that biology has in front of them. What I mean by optimization problem? Optimization problem is always a problem that basically is not, you don't want to just to maximize the gap, you actually want to maximize the ratio. Right? So sometimes in the protein folding problem, you want to optimize how good is your native state, but also you buy yourself a lot of it if you undesign possible traps. That means like reducing Tg. So it's a combination of both. Actually, when people first start designing proteins, they so over-design the proteins. When you over-design proteins, you also put traps into the system. So although these proteins, in principle, they will be the most rock solid, stable proteins known to humankind, they never were able to fold it because got in some place that never did it. So it's the idea that basically you're looking at this ratio that goes into the situation, okay? So that's, I think, where I want to put this introduction, so let's go to the next slide. Now let's think about how we move into proteins. And I think with that, I think at least you're going to see a lot of landscapes and trapping, and Dan will be talking about, Chichi will be talking about, and when you tell about these things, you put that on your background. People will be telling you about structure-based models or co-models, and it's very easy to explain that on this context. Why are we allowed to use those models? As long as you keep this on your background, on your mind. Okay. So now, how do we actually do that? If I want to get a state, if I want to get a state now that has good folding TF, how do I do that? Okay, how biology does that? Okay, how would be a good thing to do it? And before I go into these things, let me tell you one thing that is very important in a lot of optimization problems, particularly when you move to biology. Every time you have a problem that you're searching over lots and lots of states, there is what people call this problem that NP complete or exponentially complicated, that you can actually cannot find absolute minimum. Let me tell you one thing, it's not important to find the absolute minimum for protein folding. What the protein needs is to have one dominant minimum. If one minimum that kinetically reach most of the time, you don't care if there's some other funny state that you never find. Your functional state in no place is written that you have to prove that there's not another minimum. What you have to have is a system that folds to one state most of the time. That's what's required into a biological system. So it becomes a very interesting physics problem to ask you sometimes, can you guarantee that it is the absolute minimum? But in addition to the minimum, what you need is to have a robust minimum. So with that in mind, before I show this slide, I just want to tell you about robustness. That's the thing I forgot, so I apologize for that. I'll just go back to this. What do I mean by robustness? If you have a real random landscape here, and I ask you, what's the lowest state? You come say, is this one or this one? And you look around, I think it's this one. Okay, now I locate my lowest possible energy state. If I come to my interactions here, and I create a minor fluctuation on them, I may move the depth of the state, and maybe this one becomes the minimum. So if you have a real random problem like that, not only is it very difficult to find what the absolute minimum, but also it's very non-robust. Any minor fluctuation in the system. And biology, first of all, wants to have a good minimum, but also want a robust one. And that's what you're going to do. Something if you change a little bit, you always go to the same answer. So it's important to keep that in mind, because there are two things that are necessary, right? After all, we drank more champagne than we did last night, and we couldn't have all our proteins unfold and die. You're all alive here in the morning. Maybe with a little extra water, but that's all right. So there is this idea of robustness coming there. Okay. So now, let's put the idea of what we have been calling funnels, and there's a lot of discussion about it. How do we come to this idea? Again, let's imagine I could enumerate every possible state into a protein. And now I'm going to bring all the questions in protein folding, and then everybody else after me, Chichi, and then they're going to answer them. So let's at least raise what are the questions that people have. And they're very interesting questions here, as we raise them. So now what I'm going to do is, every ball here represents one of my large number of states that I have. Okay? And I'm going to just represent. The size of the balls are not important. One is my native state, is the one I want my protein to fold to. But these are all the other possible configurations the protein has. And now I'm going to organize them by similarity to my native state. Now, by the time you use the word similarity, all hell broke loose. Okay? The question is, what do you mean by similar? If you work with structural biology, most of the people define by RMSD, the root mean square deviation, right? But that's not the only one, because that's sometimes a very useful quantity, but can see sometimes a very misleading quantity. Just look at root mean square deviation, because you look at me here, that's me. If you look at me here, that's me, and that's a very big difference in RMSD. Right? So, now, what I'm trying to bring up to you is a twofold thing. First of all, on every complex system, how to define similarity. There's not only one way. And for us, similarity is going to be very important only if we can find quantities in similarity that are related to the models I'm doing. And I can use those similarity things as order parameters that tells me, and in the next step, even as reaction coordinates, where I can talk about global dynamics on a smaller number of degrees of freedom. Okay, so let's keep that in mind, because this is something you're going to hear a lot about this week, because it's a very active line of research, both into, you're going to listen on cellular level and stuff like that. How do I get a system? They have a large number of degrees of freedom, and now they're trying to collapse it into a lower dimensional picture as a question of few coordinates. And what you have to keep in mind is that it's not always you can do that. And so it's when can you do that? When you can do that in a way that makes sense. So what I'm going to tell you is that we believe that when you're...
Fiat cinza com placa de Campinas, é de alguém?
Se alguém tem um Fiat cinza com placa de Campinas, é bom correr, senão vai embora logo logo.
Tá obstruindo a rua, não? Obrigada.
Okay? So that's, as you're going to move through this week, that's going to be a very important situation. That's basically, people work in general, not only protein fold, but soft coolant patterns, things like that become, every way in physics become a way of looking for these things, but that's one thing that's going to become. Okay, so remember, there's something we call similarity. So but right now, I'm not going to go in details. I'm going to be using this coordinate Q. A lot of people will be using it. It's a very good one theoretically. This Q, instead of RMST, is the following thing. I look at my protein, and I make a list of all possible contacts between residues. So look at the amino acids, go to the structure, I say, which ones have their side chains in contact? And you make a list of contacts.